Good morning. And today we will prove that if x1, x2, x3, etc., xn is a set of linearly independent vectors in a normed space capital X, then for any choice of scalars alpha 1, alpha 2, etc., alpha n, there exists a scalar c greater than 0 such that norm of alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn greater than or equal to c into modulus of alpha 1 plus modulus alpha 2 plus etc. plus modulus alpha n. We simplify this conclusive statement by setting S is equal to mod alpha 1 plus alpha mod alpha 2 plus etc. plus mod alpha n. If S is equal to 0, then we have immediately this conclusion, because if S is 0, then this side is 0, so that norm of a linear combination greater than or equal to 0. That follows trivially because norm is greater than or equal to 0 always. So we consider the case only when S not equal to 0. So if we let S is equal to mod alpha 1 plus mod alpha 2 plus etc. plus mod alpha n, then we want to show that norm of alpha 1 x1 plus alpha 2 x2 plus etc. plus alpha n xn is greater than or equal to Cs. Consequently, if we divide throughout by S, then we need to show that norm of alpha 1 by S x1 plus etc. plus alpha n by S xn greater than or equal to C. And if we put beta I is equal to alpha I by S, beta 1 is alpha 1 by S, etc. Beta n is alpha n by S, then sigma I from 1 to n modulus of beta I is equal to 1. And then consequently, we need to show that for every choice of scalars beta I, such that sigma beta I is equal to 1, norm of beta 1 x1 plus beta 2 x2 plus etc. plus beta n xn greater than or equal to C. So we need to prove the existence of a C greater than 0, such that for every choice of scalars beta I, such that sigma beta I modulus of beta I is equal to 1, that norm of beta 1 x1 plus beta 2 x2 plus etc. plus beta n xn greater than or equal to C. And we assume that this is false. What do you mean by this is false? This is false means for some choice of scalars whose modulus sum is 1, the norm of the linear combination is arbitrarily small. So that means there is a sequence ym of vectors which are linear combinations of x1, x2, x3, etc., xn, such that ym is a linear combination of these, where sigma I from 1 to n modulus of beta im is equal to 1. But norm ym tends to 0 as m tends to infinity. That means we cannot make the norm of this greater than or equal to C, where C is a positive scalar. So however we choose, as m tends to infinity, this linear combination in one stage tends to 0. We have sigma I from 1 to n beta modulus of beta im is equal to 1 means every beta im is less than or equal to 1. Modulus of every beta im is less than or equal to 1 for all I and for every m. Therefore, for a fixed j, the sequence beta jm, beta j1, beta j2, etc. is bounded. See, you see the terms of the sequence. Y1 is beta 11 x1 plus beta 21 x2 plus etc. plus beta n1 x1 xn. Y2 is equal to beta 12 x1, beta 22 x2, etc. plus beta n2 xn. And this continues. See, if we fix a j, say for example, j is equal to 1, the terms are beta 11, beta 12, etc. See, you see the coefficients of x1 in the sequences y1, y2, y3, etc. So for a fixed j, for j is equal to 1, this sequence of coefficients of x1 is a bounded sequence. And similarly, for every j, coefficients of x2 now forms a bounded sequence, etc. Coefficients of xn forms a bounded sequence. And by Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence. Therefore, this beta 1m formed by the coefficients of x1 has a convergent subsequence. So it has a convergent subsequence, say converging to beta 1. Has a convergent subsequence converging to beta 1. So these coefficient terms converges to beta 1. Right? So suppose the subsequence which converges to beta 1 of beta 1m is chosen from the original sequence, so that its the first term is first term of the original sequence, second term is the third term of the original sequence, third term is the fifth term of the original sequence, so that the subsequence of beta 1m has is first term, third term, fifth term, seventh term of the original sequence. Then we pick the corresponding terms of the original sequence y1, y2, y3, y4, etc. So we will choose the first y1, y5, y7, y9, etc. Then that forms a subsequence of ym. Yes. So we get a subsequence y1m of the original sequence ym. Now you go to y1m. Y1m is formed by the first, third, fifth, seventh, etc. terms of the original sequence. Now you go to y1m. In y1m, we have coefficients of x2. The coefficients of x2 in this subsequence is a subsequence of beta 2m. Beta 2m is a bounded sequence. So by Bolzano-Weierstrass theorem, that has a convergent subsequence. So you take now the coefficients of x2 in y1m forms a subsequence of beta 2m. Since the sequence beta 2m is bounded, the subsequence is also bounded. That subsequence has a convergent subsequence, say converging to beta 2. Right? So this subsequence of beta 2m has now its terms from the first, third, fifth, seventh positions, etc. That has a convergent subsequence. See, suppose the terms of that convergent subsequence comes from the first, fifth, 9th, 13th terms of the subsequence or the original sequence beta 2m. Then you find a subsequence of y1m, so that is y1, y5, y9, y13, etc. of the original sequence, and write the subsequence of y2m of y1m, which is consequently a subsequence of ym, in which coefficients of x1 converges to beta 1, coefficients of x2 converges to beta 2. And we repeat this procedure. And repeat this procedure to get a subsequence ynm, which is sigma I from 1 to n gamma im xi, where this gamma im converges to beta I as m tends to infinity. So because the coefficients of x1 forms a subsequence of beta 1m that converges to beta 1. Coefficients of x2 forms a subsequence of beta 2m that converges to beta 2, etc. So as m tends to infinity, this ynm tends to sigma I from 1 to n beta I xi. And here we have, since ynm is equal to sigma I from 1 to n gamma im xi, we have sigma I from 1 to n gamma em is equal to 1. Now ynm converges to this. If we call this as y, ynm converges to y as m tends to infinity. But by our assumption, ynm, norm of ynm converges to 0. And since norm is a continuous function, whenever ynm converges to y and norm ynm converges to 0, norm y also converges to 0, or norm y equal to 0. Norm y equal to 0 means sigma I from norm y equal to 0 means y equal to 0. That implies sigma I from 1 to n beta I xi equal to 0, where these xi's are linearly independent. But that can happen only when beta I equal to 0 for all I. And that is impossible since sigma I from 1 to n beta I equal to 1. So this shows that this is impossible, so that this norm ym cannot converge to 0. That means the existence of C is proved. No such a sequence can converge to 0, or no such a linear combination can converge to 0. So all such linear combination will be greater than or equal to some C. Norm of such a linear combination is greater than or equal to some C. And that is a theorem.